Welcome. In this video, we are going to implement the DFS algorithm in only a few lines of Python code. Although we'll implement the DFS algorithm, the algorithm can be very easily adapted to BFS or A*, and I will provide in the description a link to those files where there is the implementation of the BSF on the A*. So our implementation will be generic. That means that it can work on a discretized environment, but also on continuous environment. So these are the results we'll get by the end of this video. But again, I will give the link to the code of those two algorithms as well. Let's dive directly into the implementation. Because I see a lot of very difficult implementation when I mentor students, for example. But the DFS, if you start from the pseudocode and put it directly into implementation, it is straightforward to transform the pseudocode into the implementation, whatever the language you are using. So you can keep the implementation very simple and very easy to understand, and this is what we will do in this video. So the aim is to show you that we can implement it very easily. That's a very effective algorithm, but very easy to implement. So we are starting with the game map that represents our environment, a target node V, a starting node V on a target node, which is the target. These are very generic. That means that let's say you have a game, any game, you just need to have your node V to encapsulate your nodes, your states in nodes. On the game map just needs to provide a few function calls that we'll use in a moment and that we'll review. But that means that if you create a wrapper around your environment, so that it provides those function calls, you can use the DFS algorithm as is to your games. So you don't need to change a single line of the DFS algorithm. So we start with a stack. Any pseudocode you take will have a very similar structure. You start with a stack. In the stack, you add your node V. We are not adding just the node V. We are adding a tuple with the path to this node as well. So if you want to reach node V, you just need to go to node V. So the path is not necessary, but it's useful in case because what you want by the end is the path to get from node V to target. If you do not add the path at the same time in your stack, once you've reached your solution, you don't know how to get there. That's why we need to add the path as a tuple in the stack together with the node, so that when we reach the solution, we know the path to reach the solution. Okay, so now we can create a set of discovered nodes. So basically, we need to keep track of the nodes we've already explored. We will come back to that in a moment. This is to make the implementation more efficient. It's not necessary. Without it, it would work, but it will be much more costly computationally. Okay, so while there are still elements in our stack, that means there are still nodes to explore. We loop. So while the length of the stack is greater than 0, we are looping. In Python, we're just using a list to implement the stack. We can very easily implement a stack with a list, but in other programming language, such as Java or any other programming language, you can use dedicated data structures. So what I do, I pop an element from my stack. So because I uncall the tuple in my stack, I take the node V on the path to reach this node, and then I can check if my node is already in the explored nodes. If not, I can add it in the set of discovered nodes. Doing this operation, checking if an element is in something, it's very efficient to do with sets. That's why I've been using a set. It's much slower with lists. That's why you need to be aware of data structures, and you need to add the appropriate data structures. Okay, so let's say that the node V was not discovered yet. That means we need to process it, otherwise we'll not do anything. So okay, let's process the node V. First, we need to check if the node V is a target node or no. If it's a target node, it means okay, we've found a path that was going from node V to the target node, and we can return the path to reach the target node. I'm also returning the set of discovered nodes. That's not compulsory. It's just so that I can make statistics. For example, I can check the number of nodes I've explored, and I can compare different algorithms. But what you need in your game, it's just the path to reach a target node. Okay, and then what I can do, let's say that I've not reached the target node. I still need I need to keep looping. So what I need to do, I need to take all the states that are adjacent to the node V, and I need to add them in my stack. So basically, the game map only needs this function call get adjacent nodes. So that means that again, your game map can be anything. Let's say you are let's say you have a robotic environment. You just need to provide this function call get adjacent nodes, so that you know which states your robot can reach from a given state V, and then you can plug your environment directly into this algorithm. So basically, we are making a copy of the path to reach this target node V. Then we add the node W in the path, because now we need to go to W. So we take all the paths to reach V, and then from V we can go to W. And then we add in the stack the node W as well as the path to reach this node. And then the DFS algorithm is already done. So very easy. It can be implemented in maybe maybe 20 lines of code. Very easy to do. A straightforward implementation from the pseudocode. It does not need to be more complicated than that. And then we can put all the pieces together. So I'm creating a discrete map. So that was imported from my helper. So I'm creating a 20 by 20 discrete map. Basically the one that you are seeing there. There are a few empty cells, a few others where there are some elements on the I cannot cross those elements, and I'm trying to find a path from this node to this one. So basically, I'm just calling the DFS algorithm directly on my game map that if this function call get adjacent nodes, I provide the starting node 0, 0 on the target node 19, 19. And at the end of the optimization loop, I can print the number of nodes explored, and I can also plot the path. So basically, you will get this this plot. We see that, for example, the BFS algorithm is more efficient in terms of solution than DFS for this environment in particular. It's not necessarily true for a continuous environment. So yeah, all the links are in the description in case you want to have access to the code. I also have a more detailed course about the DFS, BFS, and R-star algorithm. The link is also in the description if you are interested. Thank you for having followed this video through the end. I really hope it was helpful to you. If it was, please leave the thumbs up and subscribe for more video related to AI and to machine learning. Thank you.